And Ahmed, I'm going to give you the screen to take over while I introduce you. Perfect. So our first invited speaker is Dr. Ahmed Abdellah. And Dr. Abdellah earned his PhD in chemical engineering from McMaster University under the supervision of Dr. Drew Higgins. His research focused on developing in situ TEM techniques to understand heterogeneous catalytic CO2 reduction. Following this, he worked as a postdoctoral fellow at McMaster's Department of Chemical Engineering and as a research associate at the Canadian Centre for Electron Microscopy. His specialization was in operando liquid cell and gas cell electron microscopy to track nanoscale dynamics in electrocatalysts and thermal catalysts for energy conversion reactions, and thereby advancing the understanding of that structure-performance relationship. Currently, Dr. Abdellah holds the position of Research Associate 2 and Electron Microscopist at the Department of Chemical and Petroleum Engineering at the University of Calgary. Dr. Abdellah, thank you so much for joining us, and we're really looking forward to your talk. I'm going to go ahead and give you the reins, and you can take off.
Thank you for the introduction. Do you hear me now?
Yeah, I can hear you, and your slide looks perfect.
Okay, sounds great. So, hello everyone. Thank you for your attendance and for the introduction. So today I will present my work. Screen.
Let me know if you have any troubles.
Yeah, my screen is disappeared.
Oh no.
You still see my screen?
You stopped sharing it. Can you try sharing it again?
Yeah. Do you see it now?
I do see it, and it looks like you're about to put it in slideshow format. Perfect. That looks great.
Yeah. Okay. Yeah, so today I will present my work like in situ electron microscope for what the flow work, the technical challenging, and the lesson we learn. So I used to do working during my PhD using the in situ liquid cell, and in my postdoc I working in the gas cell. So this I will present like some of my PhD work I did it in McMaster University in the Canadian Centre of Microscope. So first I give like brief like there is a lot of operando characterization technique to studying the catalyst electrolyte interface. One of the promising technique like is in transmission electron microscope, so to studying the catalyst electrolyte interface. As they mentioned like before, like now the in situ electrochemical is now an option to watch the dynamic processing in real time. As you can see here, like we can see like this two small silicon nitrile window, and you can flow the electrolyte between them. One of this chip we can print a 3 electrode system, so you can conduct electrochemical reaction. So you can visualize like nanoparticle formation. You can visualize the dissolution of particle and agglomeration and the other stuff. And you can imagine how this chip is too small. I just put like one real image for the chip. This is a small one and the large chip. And you can see this small bright window. This is the silicon nitrile window we can assemble in the holder. So today I will talking about the workflow and the challenging we're facing during like the electrochemical measurement, especially for my work was conducting electrochemical carbon dioxide reduction under in situ TEM. So I will talking in two branches. One, first we're talking about the technical consideration you have to looking before you conduct any in situ TEM, like the liquid cell configuration, microchip preparation, how you prepare your electrode. And after that, we will move forward to like the acquisition consideration, like how we control the liquid thickness, how we conduct some analysis like EDX or yields, how you can manage the electron dose. So As they mentioned, like in the last presentation about the in situ TEM setup, as you can see here, you have the holder. In the tip, you have this assembly of two silicon nitrile window in the top of the tip of the holder, and in the back you can flow two electrolyte and they have two inlet and one outlet, and you can control the electrochemical by connecting the holder with the potentiostat, and we can control the flow rate between these two silicon nitrile window using syringe pump. But the syringe pump is good for just flow electrolyte at normal condition, but some electrochemical measurement required like saturated solution for a specific gas. In my case, I used like carbon dioxide. Carbon dioxide gas is very limited soluble in the aqueous solution, so that we have like faced some limitation to using this syringe pump in this system. So we modify the system just to replace this syringe pump by using pressurized pump. So this pressurized pump can help like to keep the solution saturated all time during the reaction. Especially we're using like very small flow rate, like 5 micron per minute. So to keep our solution, our electrolyte saturated all the time, so this pressurized pump help us to keep like this solution saturated, and we use this pressurized gas as a carrier for push the electrolyte through the microchannel tube inside the TEM holder. So to give example about like what's the difference, especially in the electrochemical environment. So when we're using like the syringe pump, and you can see here in the figure in the left, for the palladium cyclic voltammetry in situ, you can see some like broadening in the reduction peak of the palladium. This due to like once you saturate the solution with carbon dioxide and just put it in the syringe and try to flow all the solution side this microchannel with very small flow rate. By the time some oxygen can sweep inside this electrolyte and can change the electrochemical performance in the microchip. So that when we use like the pressurized pump, you can keep, as you can see here in the reduction peak in the right side, here for the pressurized pump, you can see it like it's very sharp and you are conducting in the same condition. So when this electrochemical performance, once you're doing like cyclic voltammetry in situ, you need to be sure you are working in the same condition compared to the micro scale, like for electrolyzer or flow cell, or micro scale for the electrode. So to give example, so we have like when we deposit the palladium in this microchip and also deposit in the micro scale glassy carbon, and we can see some imaging from like the small microchip. You can see the palladium decorated the working electrode, and in the large working electrode also we have almost the same shape. But when we conducting the electrochemical performance, so you can see it gives us the same feature of from the in situ as the microchip electrochemical and the large chip or the large format for glassy carbon. The only difference here you can see it like in the amount of current you have it. Like in the large format glassy carbon, you have a current around like milliampere, and in the microchip, the current is very small, it's around nanoampere. So this gives us an example. When we're doing in situ measurement, you have to be sure this working in the same electrochemical environment. The second part we will talking about it is like catalyst preparation. How we prepare the catalyst in this small microchip. So the straightforward, the most one and the easy one, just to doing electrode deposition. So you can just use the salt of any catalyst you need to do electrode deposit, and just inject it in the syringe pump and just flow it and apply electrode deposition, so you can conduct tracking the electrode deposition and the formation of this catalyst around the working electrode. So the first step, we just flow all the tube and everything with deionized water, and you can see here after like flowing like deionized water, the open circuit potential is almost like the same. After that, once you switch the deionized water with the electrolyte, in our case we're using copper sulfate, So you can see we can tracking the open circuit potential to be sure at what time all the electrolyte reach to this microchip, and all the cell will be saturated with the whole electrolyte. As you can see here, after like 600 seconds, all the open circuit potential almost be the same. So this gives us idea how like this chip is like our electrolyte is our salt reach to this 3 electrode system. After that, we can just conduct maybe like cyclic voltammetry to visualize copper deposition and dissolution. As you can see here in this picture, in the top side, when you apply like negative potential, you can see some of the copper particle starting to growing in the working electrode. And once you go into the positive scan, so this copper particle starting the dissolution in the electrolyte. So using this technique, you can tracking the formation and the nucleation of this catalyst using the electrodeposition. Other example for, as I said, like for the palladium. So you can just conduct like insert the palladium chloride in the TEM holder and apply different corona and perimetry like in different times, so you can control how much catalyst and visualize how much catalyst you want in your electrode by adjusting the time, and you can get this very localized, very clean, and very promising. But in real time, like most of the electrochemical catalysis, they're using powder form or thin film, or like just do fib and transfer it to the electrochemical cell to do some characterization. So the electrodeposition is working very well for most of the catalysts, but not for all the catalysts in the area of the electrochemistry. So that there are other types. You can just doing like drop casting or sputtering, but the issue with this small microchip, once you do drop casting or sputtering, you can't avoid just doing like some, you can deposit the catalyst or the sputtering in the whole chip, and you this can case like leakage or doing or can make like short circuit inside this microchip. So one technique just to prevent this contamination for other part, just using shadow mask. So proto chips, they have like very simple technique. They use shadow mask, so they can put it in the system as you can see here, and you can apply this small hole just to be aligned in the working electrode. After that, you can just drop casting or the sputtering, so that you can see here in this small hole, you can visualize using the light microscope. You can see, okay, now I can visualize the only area exposed to the electrolyte, the drop casting or the sputtering is localized in the working electrode. After that, you can just drop casting any powder you want in the working electrode, as you can see here in the first figure. And you can control the sputtering, how much sputtering for the catalyst. For example, you can sputter like copper 50 nanometer, you can increase the amount by increase the time. So you can increase the thickness and you can be localized in the working electrode. But one other issue when you're using the drop casting, you have to be careful about what the particle size for your catalyst. Because we're talking about like this small silicon nitrile window, there is limited space between these two silicon nitrile window. For example, if you have catalyst, let's say like as you can see here, two catalysts here, most of them like H-cast. One of them like is around nanometer, and one of them like in 3D dimension micro scale. So whatever, if your catalyst in the micro scale and even the casting in the chip, when you assemble the cell, it will be broken right away. So you have to be careful optimizing the catalyst as a powder form to be below like in 100 of nanometer or below that. After that, we need to adjust the ink to be sure like you don't put a lot of a lot of catalyst. Like as you can see here in the first image, there's a bunch of the catalyst localized in the working electrode, but this can case breaking the window when you assemble the two silicon nitrile together in the holder. So you have to adjust the ink, how much you need to drop casting by not too much to break the window, or not enough to cover the working electrode, and this, as you can see in the second image. So the second part, we will talk about like the acquisition or the challenging, how to get high quality imaging and data analysis using this system, especially if you have liquid cell inside the TEM. So one more beneficial using the pressurized pump. So if you can connect the other part for the outlet with vacuum pump, so you can control the pressure between these two silicon nitrile window, and you can adjust the thickness and avoid this blowing effect when you put this two silicon nitrile window inside the TM. As you can see, this like one paper is published before. They mention here when we adjust the pressure between two silicon nitrile window, as once you put it inside the TM, you have blowing effect. Like the liquid thickness will be too high due to like you insert this two silicon nitrile window is under high vacuum. So to adjust this or to reduce the thickness of this electrolyte by controlling the pressure between these two silicon nitrile window, you can reduce the thickness of this silicon nitrile window. After that, you can increase resolution and the data analysis you can get it from the system. The other way to play with the cell configuration. So the large chip has a specific position, you can't change it, but the small chip, you can change the position, but you can make it as a parallel configuration or cross configuration. So the cross configuration, it can give you like close to the edge, you can get like very small thin layer for the electrolyte so that you can increase the resolution. And we conduct like some small measurement to show how the cross configuration and the parallel configuration affect the resolution. As you can see in the first figure, in the parallel configuration compared to the cross configuration, the intensity per radial profile can increase more than 3 times compared to the parallel configuration. In the meantime, you can see in the cross configuration, you can still see around like 60% for the working electrode in the viewing area. So that like when you need to reduce the thickness of the electrolyte, it's better to go to the cross configuration to get like high resolution, to increase the resolution imaging when you conduct any analysis. The other part, when you're doing like as normal, like for example, carbon dioxide, you or any electrochemical measurement, you can generate a lot of bubbles around the working electrode. These bubbles can play huge impact in the resolution. So that when you generate some bubbles that you can see here around the working electrode, these bubbles can push the electrolyte toward the silicon nitrile window and reduce the thickness, so that you can increase resolution and the imaging. And this gives you one example how this we have like very thick layer, and once you generate some bubbles, you can get like increase the resolution of the imaging clearly, as you can see here in this video, and you can compare here the radial profile before the bubble formation and after the bubble formation. But you have to be careful when you introduce a lot of bubble formation. That can case like your electrolyte or your working electrode not electrochemical active. So you can just fill up the whole area with bubble. After that, your working electrode not electrochemical interact with the electrolyte. So to be sure to control this bubble, you can, or you be sure your working electrode is still electrochemical active. You can conduct like some small measurement like yields at zero loss, so you can identify around the working electrode. If you can see this plasmonic peak of the water, this can confirm, yeah, your electrode under this bubble formation is still electrochemical active, because you can see here in this figure, you can see the plasmonic peak for the water peak in the zero loss. But also you can conduct like some EDX mappings to identify all the chemical in the mapping for all the element. Like for example here, this image for the copper sputtering in the glassy carbon working electrode. So you can conduct like mapping for the platinum that connected to the working electrode, and you can see get high signal from this in the EDX, and this more challenging to get like signal in the liquid cell. But if you control the liquid thickness, so you can increase the signal coming from the EDX. And also you can easily see what's the presence for the electrolyte around your working electrode by doing like mapping for the oxygen. And the very critical point here in the oxygen peak, you can see if you're doing some spectrum here in two areas, you can see here in the area compared to area 1 and area 2, you can see strong the ratio between the silicon nitride and oxygen can give us indication about if your electrolyte is conducting with your working electrode. So if you can see close to your working electrode, you can see high signal of the oxygen is coming from your electrolyte. And in the middle of your working electrode, you can see the signal is go down as indicate like the thickness here give like the amount of the electrolyte in the working electrode is very less compared to the other area. And finally, we can also by optimizing the thickness and all this bubble formation, you can get not only for like most of the TEM and Situ TEM, just tracking the morphology change under real condition, but also you can identify the phase transformation under liquid cell, and you can get high signal from the EDX from the selected area deflection. So you can first you can try like in the platinum connector, you can under internal standard inside the each chip. So you can conduct like electron deflection in the platinum connector, and you can identify all the lattice as experimental matching with the theoretical, so that you are sure, okay, the system is calibrated, everything is working well. After that, you can apply it in any catalyst you want. For example, if you conduct it in copper or palladium, so you can identify what's the phase of this structure under real condition. And we can see one example here for the palladium. So the palladium under electrochemical condition is have phase transformation between the metallic palladium to the palladium hydride. So as you can see here, once the palladium starting to transformation from palladium to palladium hydride, the particle started to expansion, and you can see this small expansion in the lattice reflected to the diffraction, and you can identify all the phases under the electrochemical condition. By you can see here, you can conduct this measurement at different electrochemical applied potential, and you can identify here all, you can visualize all like the three phases of palladium transformation from metallic form to alpha and beta form in the electrochemical liquid cell. But the effect of the beam is very critical. You need to be sure this effect or this change, you can see it in this diffraction, is coming from the phase transformation of the electrochemical transformation, not due to the bubble formation and like the beam interaction with the electrolyte can generate hydrogen, and this hydrogen can create this palladium hydride. So to be sure, you have to, we conducting like the diffraction pattern at different overcycle potential. Now we don't apply any electrochemical potential, and we just tracking the diffraction at this small low dose. You can see here at different time, this diffraction does this change. So it gives us idea, okay, this beam dose doesn't have effect in this beam in the transformation of the palladium to palladium hydride using this diffraction. And this gives us like in the next point, the most important point when you're doing any in situ TM, just optimizing the dose rate. Because the dose rate is, you can, all the changing, you can see it, you can, using high dose rate, you can introduce some particle growth, you can get some particle transformation from phase to phase. So it is important to optimizing the dose rate. So why we say that, like you can see, we try like two different salt, like if you have some salt and you introduce some dose, let's say for very low dose, like 6 electron per angstrom per second, you can see here at the factor of time, the dose rate is constant, but the accumulated dose is built up in the system, and you can create nucleation of new particle inside the TM. And this is the only effect for the dose. And if you increase this dose like double, like to 13 electron per angstrom square per second, you can see here is this feature go very fast at very short time. And other In addition, but once you increase this to high dose, this dose can even make changing in dissolution of this particle under this condition. So prototype like give like this like action dose, so you can tracking all of this, and you can get like also like as accumulated dose as a factor for the heat map. You can see at which area starting to expose to the dose rate, like medium or high, and you can adjust the threshold your experimental at which accumulated dose you can conduct during this reaction to avoid any change from the beam dose. And you can, if you zoom out, you can get visualize which area it's exposed to high beam dose. So all in this area is just dissolution, no particle there. On the other side, if you have like medium dose rate, you get in the other area, you get cross in the other area in the yellow color. So in summary, we can use the pressurized pump to enhance the electrochemical processing in the special reaction like carbon dioxide reduction. It's better to optimizing the technique for electrodeposition or drop casting or sputtering thin film to prepare your catalyst. It's important to manage the liquid thickness and minimize the beam-induced effect to get high resolution under the TM condition. And also you can control the bubble formation to enhance resolution under the TM condition. And by coupling like the in situ liquid TM with the selected area diffraction, you can use it as a powerful technique to understanding the phase transformation under real condition. And finally, you must establish the electron dose threshold for the effect of the beam for each experimental to know the change, or you visualize under the TM coming from whatever the effect if you're doing heating or electrochemical, not due to the beam induced effect in this particle. And you can use different like tools like Faraday Cap or the Axion dose software for the dose precise dose measurement. Finally, I want to thank like all the team of the Hagen lab and all the foundation, and thank you for all for your attention.
Ahmed, thank you so much. What a wonderful talk. We've got a handful of questions for you, and you ended a little bit early, so that's good. We can probably get through all of them. If anybody has any questions too, a great time to put them in the questions box so that we can go ahead and answer them. The first question we have is, that is very promising diffraction data for liquid. What are the limitations of liquid thickness in your opinion for obtaining diffraction in liquid?
Yeah, for our experimental, like you have like we measure the liquid thickness, and there's this condition to get this bright spot for the diffraction. It looks like you have to keep it like in the range in 50 or around 50 nanometer, not more than that. So as you increase the thickness of the electrolyte, you can lose a lot of resolution.
Yeah, definitely. Okay, that's great. We get a lot of questions actually here about being able to do diffraction and eels in liquid and things, and 40-SEM in liquid, and trying to understand liquid thickness. So that's really helpful. There's a few questions kind of related to resolution here as well. And then I have my own question too. So, how are you creating the bubbles for the, for being able to increase resolution?
Yeah, so it is like other way, like for example, like under carbon dioxide reduction, as a byproduct, we introduce some bubbles. But for like other application, you can just apply very negative potential in very short time, like 2 seconds. Like you can just apply like -2 versus platinum, just 2 seconds. So you can create very fast bubble formation. After that, you can get like your analysis. But in case of carbon dioxide reduction, as a byproduct, you already introduce bubbles around your working electrode.
So you just take advantage of what you're generating already in that case. No, that's great. And so this question, were all of your, because your images were really nice, were all of your images created or captured inside a bubble, the high resolution ones, or did you use the cross configuration that you mentioned as well for some of them?
Yeah, I use both. like I use cross configuration, and I use this bubble formation, and also I adjusted like how much depend how much the catalyst you deposit in your electrode, so to choose what the spacer size you need to put it between these two silicon nitrile window. So as a proto chip, they provided different spacer in the small chip, so you can use without the spacer, you can use 50 nanometer spacer or 500 spacer nanometer between these two silicon nitrile window, and this also can affect your resolution. But you have to optimize in how much thickness your catalyst, so that you can choose what's the best spacer you can use under the TM.
Okay, perfect. That does make a lot of sense. Next question. Thank you for the nice presentation, of course. If I understand correctly, to control the bending or the bulging of the silicon nitride windows, you were also using a pressurized pump in the inlet and the outlet. Do you feel like this has added stress to the windows? Was there any additional risk of breakage? Did you test the conditions outside of the TEM to make sure there was not too much pressure? Like, what did that workflow look like for optimizing that, it sounds like? And then, did it add any increase to breakage of the windows by doing that?
Yeah, that's a great question. So for sure, like before you conducting any in situ TM, you have to doing like outside the microscope to be sure, okay, you have the correct flow rate, you have the correct pressure, so that you don't have any leakage under this condition. And you can just use very simple technique, like I use the light microscope to visualize what's happening in this two silicon nitrile window before I put it under the in situ and under the TM high vacuum, so to avoid any leakage or contamination to your TM machine.
Okay, very nice. And then I guess my question was along those lines, so I'm going to go ahead and insert it here. With the pressure-based pump, was your main purpose for introducing it and using it, if I understood correctly, was to help maintain gas saturation in your electrolyte? Was that the main reason you needed it, or was it to control the bulging?
The first main reason, just to keep our solution all the time during this measurement, saturated carbon dioxide, because the solubility of the carbon dioxide is very low in the aqueous solution. And the second reason, just like by optimizing, if you can optimize this delta B between these two silicon nitrile windows, you can reduce more this thickness or the blowing effect under the vacuum, so you can increase the resolution.
Very nice.
So for instance, you can just use the cross configuration, and also you can adjust this to pressure, so you can reduce this blowing effect.
Okay, I understand. Thank you. And then we had one more question here, and then if Sanjay is ready, we can definitely move on. So the use of the dose software was really interesting and intuitive, but being a new TEM user, how does this software compare to what was done before recording and reporting electron dose? I think what was the process like for recording dose before the software, and how has the software really helped you? Is it really that important?
Yeah, it's very helpful for me. Like before, like I did like the first paper for the palladium hydride, I just calculate the dose rate for each frame. So you collect like around 500 frame, and you have to manually calculate what's the accumulated dose for each frame. But using the Axion software, you can just get as a live show, you can see how much you get for the accumulated dose and during the session, and you already know what this, you can adjust the threshold very fast compared to doing like manually for each frame individually.
Gotcha. Very good. Very good. Yeah, it does seem to take a lot of some of the burden off of note-taking, calculations, and tracking and things like that. Wonderful. Well, if there are any other questions for Dr. Abdellah, please enter them into the questions box, maybe put his name on it, and then we can supply them, maybe relay them at the end if we've got some extra time, or we can connect you with him as well to make sure that your questions get answered. Dr. Abdellah, thank you again so much. What a really great talk.
Thank you.